Hi students, today we have a new session on classical SAR, QSAR studies and their implications to the 3D modeling. Drug design and discovery is a multidimensional task necessitating collaboration across a broad range of disciplines and areas of research. Computer-aided drug discovery (CAD) is an essential component in drug design process that accelerates drug discovery and development by providing useful preliminary information at the early stages of the process. QSAR is one of the effective data mining strategies of the computational approaches which have opened up a number of informative perspectives in modern and profitable drug design process. The chapter will introduce the QSAR studies and their different kinds of molecular descriptors, statistical methods, descriptor selection and evaluation. Similarity can be assessed directly by structural similarity or indirectly by first converting a structure to its numerical representation, that is molecular descriptors, field descriptors, and then applying one of the similarity measures. If a transformation of the structure to a numerical representation occurs, the method to assess similarity becomes quantitative. The reliability of the measure depends on the relationship between numerical representation of chemicals, that is descriptors, and activity, and this relation should be known or derived. SAR and the SAR paradox. The basic assumption for all molecule-based hypothesis is that similar molecules have similar activities. This principle follows in classic SAR is the similarity based on structural similarity. Structure-activity relationships or SAR is relation between the molecular structure and biological or physicochemical activity of chemicals. The rationale behind SAR is that the structure of the chemical implicitly determines its physical and biological properties and reactivity, which in interaction with a biological system determine its biological or toxicological properties. Therefore, the science of SAR is in relating the structure to activity, that is, identifying the key aspects of structure pertaining to the molecular events in the mechanism of action for the chemical or biological actions of interest. The direct structural similarity is a much exploited one, however, it is often unsuccessful, does not always imply similarity in activity, mainly because key aspects of the structure related to activity are not known. The SAR paradox refers to the fact that it is not the case that all similar molecules have similar activities. Quantitative structure-activity relationships or QSAR. QSAR is a mathematical relationship between the structure of a molecule and its biological activity. It can be classified as ligand-based drug design approach in the sense it is applicable when the structure of the target or receptor is known or not. QSAR methods try to identify consistent relationships between the biological properties and structural features so that this information can be used to predict the activity of novel compounds. The biological activity of a drug is the function of many factors like lipophilicity, binding affinity, water solubility, van der Waals surface area, etc., which in turn depend on the structural features of the drug. Once a QSAR model has been developed for the active compounds of a target, that model can be applied to select new molecules which fulfill the criteria. When applied to modeling of physicochemical properties of molecules like boiling point, vapor pressure, etc., it is called quantitative structure property relationship or QSPR. The QSAR relates potentity or toxicity of a set of similar drugs with a variety of molecular descriptors. One of the strong appeals of QSAR studies deals with the chemical safety and a risk of toxicity. Toxicological profile and safety assessment of new chemical entities is of paramount importance in drug design and development processes. Compounds with improved biological activity do not necessarily reach the market, and most of them are discarded from clinical trials just for toxicity concerns. Therefore, toxicity is a major source of attrition for potential drug candidates. Drug toxicity and safety assessment of chemicals is time-consuming and is accompanied with spending millions of dollars. In this context, structure toxicity predictive models of pharmaceutically relevant molecules can provide an estimation of risk assessment and safety of drug candidates, and it can be regarded as a promising and fundamental way to reduce the need for animal testing as well as ethical and monetary costs. As a consequence, potentially toxic compounds can be identified during early stages of drug discovery process. Carcinogenicity, mutagenicity, teratogenicity, hepatotoxicity, cardiotoxicity, and nephrotoxicity are the most important endpoints in toxicity evaluation. QSAR based analysis may be better regarded as an exercise to screen or filter drug candidates before they are subjected to more intensive calculations such as docking or an experimental measurement of activity in vitro, and finally under real conditions in vivo. Typically, this step will pick up a dozen of drug candidates from a library of millions of well-studied molecules. Utility of the QSAR approach includes prediction of property or activity, refinement of synthetic ligand. It can suggest as to what type of, say, a side chain modification will improve or decrease the bioactivity of a compound, etc. The input for such a study is the structures of molecules known to possess certain biological activity and their bioactivity profile. The activity profile needs to be generated by experimental work and most importantly should be in quantitative terms. A minimum of 20 compounds known as the training set with varying levels of biological activity is needed to derive a valid QSAR equation. The evolution of QSAR. The main impact on development of the concepts of QSAR was from the work of Hammett in 1937 and Taft in 1952, which discussed the effect of functional group substitution or replacement on organic reactions. These contributions constitute together the mechanistic basis for the development of the QSAR paradigm. Corwin Hansch's research publications in 1960s about the relationship of plant growth regulators and their dependency on Hammett constant and hydrophobicity laid the foundation of QSARs. The Hansch analysis introduced a way to predict the biological activity from theoretically derived molecular descriptors. Hansch and co-workers investigated the possibility of expressing a relationship between structural and physicochemical properties and biological activity quantitatively. Hansch equation. In the Hansch analysis, the biological activity log 1 by C was correlated with the descriptors using multiple linear regression. The Hansch equation is given as log 1 by C equals minus A into log P the whole square plus B log P plus C sigma plus D E A plus E, where A, B, C, D and E are the constants obtained through statistical analysis of the data. Hansch equation can relate biological activity to most commonly used physicochemical properties log P, pi, sigma and a steric factor. Biological activity, that is IC50, LD50 concentration required to give specified effect is related to a combination of physicochemical properties. It is a linear free energy relationship. If a symbol equation involving only a few parameters, the others are kept constant. A typical QSAR would look like equation 1 derived from the training set, from which the constants would be calculated. Since the molecular descriptors log P partition coefficient, sigma the negative value signifies that it is an electron donor. EA are dependent only on the structure. Calculating these descriptors in silico and substituting in the equation would give the activity of the compound, whose biological activity has not been tested. But the accuracy of the prediction depends on the accuracy of the biological data of the training set. Some typical QSAR applications include calculation of single molecular species properties like boiling point, vapor pressure, critical temperature, flash point, melting point, refractive index, density, viscosity. Second, interactions between different molecular species like octanol water partition coefficient, aqueous solubility of ligands and solids, etc. And third, biological properties such as sweetness, correlations, mutagenicity, general toxicities, allostatic activity, etc. All QSAR techniques assume that the compounds interact with the same biological target in a non-covalent manner, that is, hydrogen bonds, hydrophobic and hydrophilic interactions. The interaction of similar structured compounds is similar with the functionalities in the binding sites. This assumes a rigidity of the interacting system with no molecular dynamics to consideration. The best QSAR relationship will be obtained with closely related active molecules, all having the same mode of action. A good spread of activity in the test set to improve statistical validity. An assay which is close to the site of action, example binding or enzyme assay. The biological activity is usually expressed 1 by C, where C is the desired concentration of the drug to achieve a defined level of activity. Inverse, because more potent ones achieve the level at much lower concentrations, or IC50. Drug concentration that is required for 50% inhibition in vitro, or EC50, which is the plasma concentration required in obtaining 50% of a maximum effect in vivo, depending on the type of assay. Molecular descriptors. Many descriptors can be calculated rapidly using empirical formulas based on the structure and the connectivity of atoms in the molecule. For example, descriptors such as the molecular weight and the number of H bond acceptors are easy to determine. Some descriptors such as log P and molecular polarizability can be approximated from atomic or group contributions. Molecular descriptors are numerical representations of molecular structures derived from steric, electronic, constitutional, topological and geometrical properties of the molecules. Descriptors used in QSAR hold information about a molecule either as a whole or distinct parts of it. These descriptors in hand, those with biological relevance, should be selected. The molecular descriptors are divided into two main categories: experimental measurements such as log P, molar refractivity, dipole moment, polarizability and in general physicochemical properties, and theoretical molecular descriptors which are derived from a symbolic representation of the molecule and can be further classified according to the different types of molecular representation. The main classes of theoretical molecular descriptors are the OD descriptors, that is constitutional descriptors, count descriptors; 1D descriptors, that is list of structural fragments or fingerprints; 2D descriptors, that is graph invariants; 3D descriptors such as for example 3D Morse descriptors, WIM descriptors, getaway descriptors, quantum chemical descriptors, size, steric, surface and volume descriptors; 4D descriptors such as those derived from grid or COMFA methods, Waals surf. The most important of these are steric descriptors related to size and shape of the chemical, electronic descriptors related to the ability of the chemical to undergo reactions, and the polarity descriptors, water immiscible, related to transfer across cell membranes. Hybrid descriptors. They are generally combinations of electronic or topological or geometrical descriptors and in general characterize the distribution of a molecular feature over the whole molecule. Examples include the charged partial surface area (CPSA), hydrophobic surface area (HPSA) and hydrogen bonding descriptors. The importance of these descriptors is that they provide localized information regarding molecular features. The aim and utility of QSAR studies are to develop quantitative structure-activity relationships, predict the properties and activities of untested molecules, optimize the properties of a lead compound, compare different QSAR models statistically and visually, generate hypotheses about the characteristics of a receptor binding site, validate models of receptor binding sites, prioritize compounds for synthesis or screening. Steps involved in QSAR study. The descriptors are calculated. Secondly, the best descriptors from a larger set of relevant descriptors are identified. Molecular descriptors are mapped into the biological activity, wherein the relationships can be often complex or linear. The model is validated to determine its predictive ability and to generalize to new molecules that are not in the training set. QSAR methodology covers data analysis and statistical methods for developing models with capability of predicting the biological and toxicological activities of compounds based on their structures. Different descriptor selection methods aim to determine the best descriptor subset from a large pool of descriptors have been proposed to reduce the number of descriptors present in the final mathematical QSAR model for explaining the biological activities of the studied molecules. Descriptors are generally selected in one of two ways. Firstly, it can be a presumption search, wherein descriptors which might yield the best model for the property in question is chosen on a criterion. Secondly, a large number of descriptors, perhaps several hundred, are generated and a statistical method such as stepwise regression or principal component analysis or genetic algorithm or method of partial least squares is applied to select the best descriptors, that is, those that give the best correlation with the property in question. Statistical methods. Some of the statistical methods used in QSAR analysis are principal component analysis or PCA, partial least squares PLS, stepwise regression methods, genetic function approximation or GFA, and simulated annealing. Types of QSAR methods. QSAR methodologies can be broadly divided into three groups. First, 2D methodologies do not consider the 3D structure of a molecule directly. Instead, the molecule is represented by a set of molecular descriptors, numerical values characterizing various aspects of molecular structure. Together with the observed activity, a predictive model is built. Two-dimensional approach has a number of advantages. First, owing to the variety of molecular descriptors available, optimized coordinates are not always required. In fact, connectivity information in the form of smiles, strings or an adjacency matrix alone can be built rapidly for very large sets of molecules. Second, this approach avoids the alignment step and thus can be used in the absence of experimental information regarding the binding of a molecule to its target. The downside to the 2D QSAR methodology is that it does not provide a detailed answer regarding a molecule's activity. That is, representing structural information in the form of descriptors, the aspects of a molecule's activity such as its absorption and degradability properties are hidden by a layer of abstraction or not addressed at all. Thus, a molecule might be observed to have low activity. A 2D model may not be able to indicate whether this is due to its inability to bind to the target or whether this is due to cross the cell membrane. The point is that in a 2D QSAR model, a lot of information about various aspects of a molecule's activity are combined together and are not always individually apparent. Though interpretation methods for linear QSAR models exist, they are obviously restricted to the information encoded by the descriptors in the model. This means that though 2D QSAR models are certainly very useful, especially for screening purposes, they should be used in conjunction with other types of models to fully understand the role that various structural features play in determining the activity of a molecule. The second type of methodology is 3D in nature and is exemplified by the comparative molecular field analysis approach. Molecular fields basically are 3D representations of the steric, electrostatic and hydrophobic surroundings of a molecule. A molecular field is generated by enclosing the molecule in a 3D grid and assigning non-bonded interactions between a probe atom and the molecule in each grid point. Obviously, the difference between two different types of fields is the algorithm with which the non-bonded interactions are calculated. It is of importance because they allow for the simulation of directional forces, hydrogen bonds, metal ligand contacts, polarization effects, and interaction between electric dipoles. Such forces are known to play a key role for both molecular recognition and selective ligand binding. In the figure given, 3D QSAR, a probe atom is placed at each grid point in turn method. Measure the steric or electrostatic interaction of the probe atom with the molecule at each grid point. In simple definition, COMFA takes the 3D conformations of the molecule into consideration. Hence, several crucial items needs to be considered. First, in order to find low energy conformations, or rather the global minimum energy conformation of each compound under investigation, conformational analysis is conducted. Second, all molecules must be aligned in the same coordinate system, and several options to perform this are possible. For example, if a pharmacophore is available, one might choose to superimpose all molecules on mutual and likely interaction points with the receptor. Third, molecular fields are generated first when the molecules are properly aligned. COMFA studies result in contour plots, steric and electrostatic. This type of output would give a direction to the synthetic chemist as to what type of modifications in the basic structure of a molecule would result in enhancing the activity or otherwise. 4D QSAR. The 4D QSAR methodology is an extension of the 3D QSAR methodology developed by Hopfinger, which considers conformational information as a fourth dimension. Similar to the COMFA method, 4D QSAR starts off by defining a set of grid points on which molecular properties will be evaluated. In addition to the grid points, the method performs conformational ensemble sampling and uses the information obtained to evaluate interaction pharmacophore elements, or the IPEs. The IPEs together with the molecular properties are then used to develop a quantitative model to forecast activity. The approach is termed as RD-3D QSAR analysis. Thus, the 4D QSAR scheme can be applied to both receptor-dependent and receptor-independent problems. The fourth dimension of 4D QSAR analysis is the dimension of ensemble sampling. In 3D QSAR, where each ligand molecule is represented by a single 3D entity and is the identification of the bioactive conformation, orientation and possibly the protonation state is a crucial step in the procedure. If the underlying pharmacophore hypothesis is based on incorrect assumptions, the resulting surrogate is hardly of any use for predictive purposes. In explicit 4D QSAR approaches, the ligands of both training and test sets are provided as an ensemble of conformations, orientations and most importantly protonation steps. The most likely bioactive representation is then genetically evolved from the reservoir using a Boltzmann weighted selection criterion. Now let us summarize the session. It is assumed that molecules having similar structure will have similar chemical properties. Hence, the information provided by a compound or set of compounds known to bind to the desired target is used to identify new compounds from the external databases of chemical compounds using virtual screening approaches. This chapter takes the cue to discuss much more about the most commonly used methodology for ligand similarity based lead identification, quantitative structural activity relationship QSAR, and their structural molecular properties. Before we attend the next session, please try to answer the following questions. 1. Briefly discuss about SAR and SAR paradox. 2. Define QSAR. 3. What are molecular descriptors and its types? 4. Mention the types of QSAR. Here are a few books for your reference purpose. Bioisosteres in Medicinal Chemistry by Nathan Brown by Willy VCH Publications. Computational Structural Biology Methods and Applications by Schwede T. World Scientific Publications. And Lead Generation Approaches in Drug Discovery by John Wiley Publications. Thank you, students. Thus, we come to the end of the session. Hope to see you next time. Thank you and goodbye.